So chapter 3 is all about functions and their graphs. I think last week I referred to this as a menagerie of functions and graphs. So a good place to start would be with talking about what is a function. In order to describe a function, we first need to define a relation. So a relationship is a correspondence between a set X, that's our independent values, called our domain, and a set Y called our range. Remember, our Y value is our dependent variable. So in reality, a relation is any set of ordered pairs. A function from X to Y, so our function maps our domain to our range, is a relation where each X value has exactly one Y value. Okay, so each X has exactly one Y value. And the best way I've figured to describe this is with a vending machine. So a vending machine functions, right? You push a button, you get a snack. So all those buttons, those are going to be our domain, right? So I could push C7, I could push D6, I could push E4, right? I push a button and I get out a snack. Those snacks are our range. So I don't know why there's an apple in there, but we could put an apple. We could get some chips. We could get M&Ms. Okay? So the way a vending machine works is I put in money, but we're skipping that part. If I push C7, I get an apple. If I push D6, I get chips. If I push E4, I get M&Ms. In this case, each X has exactly one Y value. So this is a function, right? I wonder though, would my vending machine still work if I had C7 and D6 both going to apples, because we're trying to be super healthy, and E4 go to M&Ms? And chips is all lonely and nothing maps to it. So it's really not in our domain. In our range, would this still be a function? Yeah, right? I push C7 and I get an apple. I push D6 and I get an apple. The machine still works. Each X still has exactly one Y value. So this is a function. So how could I make our vending machine not function? How could I break our vending machine? Well, I've got my 3 buttons. And what if I had C7 go to apple and to chips, and E4 goes to M&Ms? Now, if I push C7, what happens? Do I get back out an apple and chips? No, the vending machine company doesn't want you to get 2 snacks for the price of 1, right? This would cause our vending machine to break. It's not going to give you anything. This X value has more than one Y value. It has 2 to be exact. So this is not a function. So relations and functions can be defined not only as a set of ordered pairs, but it could also be a table, a graph, be that a graph of an equation or a nice little picture like I drew of a vending machine. It could also be an equation or a rule. So for example, this linear equation, where I'm going to show you why all linear equations of the form y equals mx plus b are indeed functions as we go on in this section. So friendly reminder that the domain is all possible values of our independent variable x, and our range is all possible values of our dependent variable y. So we've got our domain and our range. So let's state the domain and the range of each of these functions, of each of these relations. These are relations, we don't know if they're functions, and determine whether or not they're a function. So let's take a look at f. So for f, the domain, I'm going to represent this with a D. Its domain is all of its x values, so 1, 4, and -1. Typically we like to write those from smallest to largest. And its range is 2, 5, and -2. I'm going to represent this with a beautiful little picture, just like we did our vending machine, where I've got my domain on the left and my range on the right. I have that 1 goes to 2, 4 goes to 5, and -1 goes to -2. This is a function, right? If this was a vending machine, it would still work. Let's take a look at G. Where am I going to put G? We'll put G down here. G has a domain of -3, -2, -1, and 0. I'm so creative, guys. And its range is 5. Well, I already picked up a 5, right? In sets, we don't write elements twice. That's what these brackets are. Sets 5, 4, and 1. So let's do 1, 4, 5. And I want to know, is this a function? So I'm going to go ahead and graph my domain to my range. I have -3 goes to 5, -2 goes to 5, -1 goes to 4, and 0 goes to 1. Does this vending machine still work? Yes, this is a function, right? If I push -3, I get out of 5. If I push -2, I get out of 5. Each x has exactly one y value. Last but not least, let's take a look at h. H has a domain of -1 and -2. Because if it is repeated twice, I don't write it twice. Its range is 0, 2, and 1. So I've got my x's, which are my range, and which are my domain, and my y's, which are my range. So -1 goes to 0, -2 goes to 1, and -2 goes to 2. Does this vending machine work? No, because this x value has 2, count them, 1, 2 y values. So this is not a function. But like I said, sets of ordered pairs are not the only way to define a relation. We could also define it with a graph or an equation. And we've been working a lot in this course with linear equations and quadratic equations and circles, and basically we're learning how to graph everything. So what we can do is use the vertical line test to tell if the graph of our equation is indeed a function. So the vertical line test says that each point of a graph of a relation, so a set of ordered pairs, that's what these are, sets of ordered pairs, right? Just defined by an equation. Each vertical line will intersect at exactly 1 point. Or no more than 1 point, it could be 0. So here, this passes the vertical line test, this linear equation right here, y equals mx plus b, because for each line, it intersects, for each vertical line, it intersects our graph only once. The same thing is true with this parabola. It also passes the vertical line test. Some things that don't pass the vertical line test are this bad guy right here, right? This is like a rotated parabola. Right here, it has an x value of 5 that has a y value of 2 and -2. So this is not a function. Same thing is true for our lovely friends, the circles, right? Those are not functions. So that's why I've been trying to express why it's so important for you to visualize what you're graphing and what the function is you're working with, because pretty soon we're going to learn some really cool things that only apply to functions. So let's take a look at these 3 equations, and I want to ask, is it a function? So what I want you to do first is visualize, what do these look like? So I have y equals -3/5 x plus 2. Okay, that's going to be the graph of the line. It's going to be a line with negative slope, and it's going to be a function. For number 2, that's y equals x squared plus 3x plus 4. This graph forms a parabola, right? Shifted somewhere around our xy coordinate plane. But parabolas are functions. They pass the vertical line test. Last but not least, I have 3x plus y squared, 3x squared. For number 3, I have x squared plus y squared equals 6. Darn tootin', this is a circle. Its center is 0, 0. Its radius is the square root of 6. It fails the vertical line test, so this is not a function. Exclamation point. When an equation is a function, we can rewrite it using function notation. So instead of y, we will use f of x. That means it's a function that depends on x. X is our independent variable, and our y values that we graph depend on that. So we could say y is a function of x, and we use this notation to emphasize that it's a function. So each x has exactly one y value. So it has special properties we're going to talk about later. And it's really just another name for y. So that's something to keep in mind. So friendly reminder that linear equations are functions. Their domain goes from negative infinity to positive infinity. Their range depends on how they're defined. Quadratic functions are also have a domain of negative infinity to positive infinity. Their range depends on where they're located on our xy plane.